Once you completed the project mission statement and then the target specifications of the product that you are planning to develop, then you can move on to the next level or next phase of product development process, that is product concept generation. So the concept generation is the most creative phase of any product design exercise. In general terms, a concept is an idea that is sufficiently developed to evaluate the physical operation of the intended product. So the concept need to satisfy established needs and specifications of the product. So in the concept development process, initially you'll have to look at the existing products. In fact, you have already done to some extent during benchmarking exercises that you have carried out. And then there are some methods available that would help this concept development process. So you could follow these methods. So I will introduce those methods during this lecture. And once you came up with certain concepts, ideas, then you could represent these ideas, the initial ideas, using sketches, as you can see here in this particular picture. Product is a blender, and different sketches have been developed for different ideas. And then, of course, you can use if you want a 3D CAD modeling tool like SolidWorks to model your ideas. But of course, initially we prefer to come up with some sketches, and then some selected sketches can be drawn in, can be modeled in SolidWorks to further investigate. And of course, in addition to sketches, a concise description of how the product will satisfy the customer needs, etc., need to be expressed so that the decision making would be easy. If you look back, the generic product development process that we looked at in our first lecture, once you complete the planning phase, you will get the project mission statement and also the customer needs and the target specifications worked out. Those are the inputs to the concept generation, concept development phase. So during this phase, of course, we are going to generate several potential solutions to the problem that you're going to solve. And usually this starts with generating many ideas, many concepts, maybe 50-60 concepts. But out of those, through several brainstorming sessions, we try to identify a few potential solutions. For example, 5 to 20 potential solutions for further consideration. And of course, this phase is very important. Usually in any product development exercise, about 5% of the budget is allocated for this concept development, and about 15% of the full project time is spent on the concept development. So this is a very crucial phase because all your innovative inputs are coming into the product at this phase. Therefore, you'll have to take this phase very seriously. And once the several concepts are identified, several potential concepts are identified, then we move on to concept selection. That is the part 2 of the concept development phase, where we try to find one particular solution, one particular promising solution, and that will be further investigated during the rest of the period. So there are techniques again for concept selection. So that will be discussed later. And it is general understanding that a good concept can poorly be implemented if you have not followed the techniques up in phase 2, phase 3, phase 4, and phase 5. Even the concept is good, it may not be effectively implemented. But again, if the concept is poor, there is a very hard chance that you could get a commercial success for your product. Therefore, identification of right product or right concept is very important for the success of the entire product development exercise. Now, the concept generation is basically starts with the mission statement, customer needs, and target specifications as inputs. And the goal here is to you become confident that full spectrum of options have been explored. That means you look at the entire problem in a very open mind and look for all possible scenarios that you could consider as potential solutions. And then as a result of that, you will be developing set of possible concepts and you will represent them using sketches, as you can see here. And of course, this is a creative idea generation process. And for the same purpose, there can be several different solutions. As you can see here, these are peelers, and different companies have come up with different different products, different products with different appearances. Most of them serve the same purpose. So it's kind of creative idea generation process, and different individuals would look at different individuals will come up with different ideas, different solutions for the same problem. If you look at the creativity and innovation in general, creativity is more or less a characteristic of a person, his ability to generate new ideas, alternative solutions, and possibilities in a unique and different way. I hope all of you know late Mr. Steve Jobs, who was the former CEO of Apple Incorporation and who was regarded as a pioneer in creative product development, who helped the Apple company to regain its pride with series of very innovative type of products. And of course, according to him, creativity is just a connection of things. It's like when you see something and with your experience you connect things together and come up with new ideas. It's not just like some idea pops into your mind on your own kind of activity, but it's a more or less a kind of a connection between your mind and what you see. So innovation is when you have ideas and putting these ideas into action is more or less the innovation. So that is more or less the engineering part of it. So when you have a fancy idea, and the way that you implement in real terms is more or less the innovation. So innovation is connected with technology, different new product lines and segments, new methods of production, and improvement of existing products and things like that. Creativity, invention, innovation has been identified as a kind of a very important attribute a 21st century engineer should possess with. So that therefore the development of some skills required to be creative and innovative is very important for a future engineers. In creative product development, the visual thinking is one of the most important skills that you need to develop to be creative. It's more or less seeing things, and then model things in 2D or 3D, maybe sketches or maybe 3D models, and then imagine adding new things. You just imagine things, and then you see things, and then you connect them. You present them using 3D models and see how they work, and then do some further improvements, and then look at it again. Like that, it goes in a cycle, as you can see here. Seeing, modeling, and imagining is other key elements in visual thinking process. And brainstorming is also a very important exercise that we carry out in creative idea generation processes. Uh, of course, I discussed about this brainstorming in my previous lecture. This technique is mostly when you do some group activities. The brainstorming is a very effective tool that helps us to combine different ideas of different individuals together and come up with some creative, useful ideas. And similar to brainstorming, there is another technique called brainwriting. The main difference is basically in brainstorming, you collectively discuss and make your own decisions, but in brainwriting, you independently develop ideas and then you come together and then with the discussion of the members of the group, you further improve it and drop certain ideas, add few more ideas, and come up with new concepts. So with that, let's look at concept development process. Basically, it's a 5-step process. Initially, we try to understand the background of the problem. So we try to clearly understand what the problem is at this time. And after that, we try to decompose the problem into several sub-problems. And then we try to identify critical sub-problems so that we could start uh, developing ideas. And once you identify the sub-problems, of course, you can start generating ideas, new concepts to implement these sub-problems. For that, you can search externally. You can look at what others have done in solving similar problems, or then you can search internally. That means you can discuss among yourself, the development team, and come up with some new ideas. Then you can converge these ideas coming from 2 different routings, externally as well as internally, existing concepts. Then from internally you get some new concepts developed by yourself and put them together and explore these ideas systematically using certain systematic tools, and then you can decide on what your final product is going to be. Of course, at this level, we are going to look at several alternative ideas, and then always once you come up with some idea, you'll have to go back and see whether you have included all necessary requirements in that idea. So that is basically the 5-step process of concept generation. So we'll look at each and every step of this process little in detail and look at what are the tools available for us to do these investigations at different steps. Now, the step 1 is clarify the problem, so further understanding the problem. Of course, once you complete the phase 0, that is planning phase of the product development, then you have this mission statement and customer need list, and then again target product specifications. So those will explain what the problem exactly is, but of course those are inputs. And as a tool, of course, you could use quality function deployment technique to make sure that you have understood the problem completely and you have considered all necessary requirements in your customer need list in developing your specifications. The QFD technique that I introduced you in my previous lecture enables you to understand the design requirement. It forces you to think in deep about the problem and come up with some alternative ideas to implement certain problems, certain solutions. And also you could use this as a design tool as well as a communication tool to communicate your ideas with the other third parties. You could include this diagram, QFD diagram, in your report so that anybody who looks at it will be able to understand how this product has been developed, what kind of factors have been considered in this development. And of course, it helps us to decompose the problem into sub problems, subcategories, manageable subcategories, which is essential thing in the product idea generation process. So I'm going to explain this in detail in the coming slides. So if I look back the quality function deployment technique, for example, if you take this one of the previous examples that we looked at, learning station, an interactive learning tool for children, school children. And I'm not going to explain this again, but just for the sake of understanding this, of course, these WATs that are mostly customer needs. You identify these during customer need analysis, and then of course these are the specifications, how we are going to address these customer needs. These also you have identified already at this level, target specifications. And then again you calculated most of you calculated using HP technique importance of each customer need in the product. And so these things you have already identified, and this QFD technique helps you to analyze and find out the importance of each specification in the product. So what specification is more important than the other specification, for example, relative importance of each metric. And then of course using this technique you can come up with something called completeness. That is how effectively you have addressed the customer needs in the specifications. The numbers that are shown here, higher the better. So if you have a high number, that means you have addressed that customer need very well in the specifications. Or if you have a low number, then again you have not addressed that particular customer need quite well in your specifications. But of course, as you can see here, some customer needs are relatively less important. So in that case, it will be okay to put relatively less attention on this kind of customer needs in your final analysis. Again, it's your choice, but by looking at this completeness values, you can quantify how well you have addressed the customer needs in your specifications. Now, the metrics that that you fill up, that is customer needs against the specifications, is the relationship metrics. As I said earlier, this relationship metrics. The relationship metrics indicates the strength of the relationship between the customer needs and the specifications. Of course, you can populate these metrics during your brainstorming session. And one way of populating this is indicating at each element whether that relationship is a high or medium, low, or there is no relationship, for example. And we assign numerical values for analytical purposes for high, medium, low. For example, high 9 points, medium 3 points, low 1 point, and if there is no relationship, the blank, which is 0. And these are the typical values that we assign for these H, M, and L, L's in this relationship matrix. Alternatively, some books we find symbolic representation rather than H, M, and L. These are the symbols, as you can see here, and the numbers that are assigned, of course, more or less the same. So these are typical numbers, so you could use the same numbers. And of course, for each specification, it is always good to have at least one H in this column. Each specification should address at least one of the needs at a high level. You fill up this relationship matrix during your brainstorming exercise, and then based on that, of course, you can fill the rest of the fields, technical weights, and the completeness. If you look at the technical weights first, uh, the technical weights, absolute technical weight values are calculated according to this simple formula, where Rkj is the element of relationship matrix, element value. They use H9, M3, L1 and blank 0. And Ak is the relative importance, the value over here. And you sum them up together up to a number of needs. And then you will get the value here. For example, if you look at this number, that is H, importance is 5, so 9 into 5, and this one medium means 3, and the importance is 3 into 3, and this is H means again 9, and importance is 1, 9 into 1. When you sum them up, what the number that you get is 63. And then of course you can add them together, all these values. You can do this for each column and add these numbers together. So for example, you get 389 in this particular exercise. And then you can calculate the relative weight values, in terms of percentage. For example, over here the absolute value is 63, the total is 389, therefore this is 16%, as you can see here. And then again you can identify the highest number over here, and you can normalize everything to this highest number. And if you use 5-point scale as we discussed earlier, then you can assign 24% 5, and then accordingly proportionally you can find the numbers, important values of importance for this. For example, for this column, this 24 is 5 and 16 means 3. So you can calculate these values for each and every row just like this. And then you can move on to the completeness calculation. So the completeness is calculated using this particular formula, as you can see here. AI is importance again, and RLI is element of relationship matrix, and L goes from 1 to M. It's number of metrics. So if you add them together, for example, this one HL, ML, HM, and importance is 5, so it will add to 130. So 130 is relatively large value, therefore you can conclude that this particular need is addressed well in the specifications. But if you look at this one, for example, number is quite low. That means you have not well addressed that particular customer need. But again, that customer need is of course not a very important customer need. Therefore, as a team, you can discuss and agree on whether to accept this particular this particular set of specifications for customer needs, or whether you want to do certain modifications to improve the completeness numbers. In the roof, we basically indicate the interdependency of different metrics. For example, if the weight as well as the cost are two different metrics in one of the product development exercises, then of course when you reduce the weight using expensive lightweight material, the cost will go up. So they are when you increase one, other will get decreased. So they are negatively related like that. There can be situations where certain specifications are positively related. When you increase one, another one will also get increased. And of course, there will be a degree of dependency. Some are highly dependent, some are less dependent, like that. So dependency can be represented using some symbols, as you can see here. So this is positive dependency, and this that means improving one specification improves another, and this is a strong positive dependency. So that means there is a huge increase when you increase one thing, and then there can be negative dependencies, etc. You could use this quality function deployment technique to represent all these information, and once you represent all these information and do these calculations, then you will get a complete understanding about the problem. So this is a very important technique that you could use to understand your problem clearly and make sure that you have considered all aspects in a fair way in your list of specifications, and now the product is ready for development. So once you clearly understand the problem, then you can go for problem decomposition, that is dividing a complex problem into simpler sub problems which can be tackled, which can be handled at the development level. And there are several methods that we could use for this. Functional decomposition, which is the most common method. We divide the entire problem considering the functionality of the product, and then there can be ways of decomposing based on the user actions, how a user could use this particular product. And again, you could use decompose a problem by considering key customer needs. So there are several ways, but of course at this level we are going to concentrate on functional decomposition, which is the, as I said earlier, which is the most common method. So the decomposition is more or less divide the problem into several sub problems. For example, a simple problem, non-engineering problem, if you look at like making a breakfast. So to make a breakfast has two parts. You have something to eat and a cup of tea to drink. So you can divide it into two broad sub problems. And of course, making toast or the bread toast, you can further divide into several sub programs, sub problems: slicing bread, toasting, butter, apply butter toast, and jam, etc. And the making cup of tea also, you need to do certain activities, certain functions are involved: boiling water, brewing tea, and adding milk, for example, and also adding sugar and things like that also can be considered. Likewise, we are going to decompose our problem into small functions which can easily be handled in the development level. Now, if you look at one of the case studies given in this the standard reference that we'll be using, this coil roofing nailer, that is a replacement of a hammer, a mechanized nailing machine, where you can use this to draw nails into mostly wood instead of using a hammer. Now, in this case, they have identified major customer needs, what customers expect from a nailing machine, and then they have indicated certain assumptions. For example, now if you are developing a bicycle, for example, then some parts of the bicycle, of course, you will have to buy from the market. For example, tires. You are not supposed to make tires. It's a very difficult process if you want to make your own tires, and if you want to make a custom order from a company for tires, then the tires will be very expensive. So you'll have to assume that your rim size is compatible with the tires available in the market. Just like that, they have identified compatible with the existing nail magazines. So you can buy existing nail magazines from the market and plug it into this one, for example. And it, likewise, there are a couple of more assumptions they have considered. And then again, they have come up with specifications. In the specifications, they have clearly identified the technical aspects in a quantifiable manner. For example, maximum nailing energy is of 40 joules per nail. It needs 40 joules a nail, and the nailing force is about 20 kilonewtons. And they want to make 12 nails per minute. 12 nails per minute, like that. So, and then they have come up with some specifications, some features of the product that can be considered in the development phase, idea generation phase. For example, now they have combined this nailing energy 40 joules per nail and 12 nails per minute. So these are very technical descriptions. A customer could not be able to understand these highly technical terms. Therefore, you can combine these two statements, for example, and come up with something which can be understood by the customers, like a DC motor driven one you use just like you use the DC motor of 650 watts of power, which could deliver the required energy. Functional decomposition is of course a two-step process. So in the first step, you look at the problem as a black box. You don't look at the details, just one unit, and then you identify three inputs: energy, material, and signal. So in this case, the energy need to be decided, and the material is of course the nail, and the signal is the signals that you send to the tool. So whatever the problem, the three things that you need to identify: the energy, material, and signal. So and then outputs are also energy, material, and signal. So the types, what we are going to do, we'll have to work out during this. Now in the next step, you divide this into sub functions. Now the sub function, for example, for energy, the sub functions, you'll have to either use a battery or you'll have to plug it into the mains. So you can consider it as store or accept external energy, and then you have to convert energy from electrical energy to mechanical energy. For example, there has to be certain energy conversion, and then this energy need to be applied to the nail to draw the nail in. So this is the energy flow, and as a result of that, you can drive nails. And then again, nails, the material, in this case nails, then you'll have to have a nail magazine, the storage, and then to drive a nail into something, then you have to isolate nails. You have to take one at a time and apply energy. So the nail isolation, and then again the signals. So you have to sense and then have to trigger the tool to apply the necessary force on the nail to drive it in. So so this is the functional decomposition of this particular particular case, and this is more refined function diagram showing sub functions. So of course, this identification of different sub functions you can discuss among yourself, and you can organize a brainstorming session and decide what kind of sub functions that you could consider in this particular problem that you are dealing with. And also please make sure that the indications in these sub functions as in this level were not considered any physical solution concepts. For example, store, we are not going to say it's a battery or fuel cell or engine or anything like that. We are not going to say. We'll just store. So it's store or use external energy. So it's a very open statement where the next level you can discuss and decide, explore what kind of options that you could have for storage. So at this level, our goal is to describe the function elements of the product without implying specific technological working principles. So we are not going to look at the technology. We are going to describe the functional element in general in a very open statement. This analysis is going to be very difficult if you have a large number of subprograms. You will soon realize when you look at some analytical tools. Therefore, you have to limit this one at maximum of at least 10. So if it is more than that's going to be very difficult. So too many sub functions will make this decision making process very hard. Therefore, do not try to understand hundreds of sub functions. Try to limit the number of sub functions maximum of 10 in your problem. Now, this most of these techniques that we discuss under this product development in general are not very concrete descriptions. So, like in an analytical problem solving, like application of Newton's law or something like that, uh, there is only one unique solution. But in exercises like this, there is no such one unique solution. It's the way that you look at it. So now you have the freedom to decide things, and of course, when you make decisions, you need to make a clear justification. Otherwise, you yourself will not be able to be convinced about the decisions that you make. There is no single correct way of creating functional diagrams or functional decomposition. It's up to you, but of course, you can consider the things that I just mentioned uh, to do this exercise effectively. Uh, to start this functional decomposition exercises, of course, some useful tips that I could give you. You could initially start with an existing product. Since you don't know exactly what your product is going to be, then you can think about a similar existing product and try to decompose that product and then tune it up to the ideas that you have later on. And or you can, if you have several product concept ideas, and then you can arbitrarily pick one and do the decomposition, and then through continuous iterative process during your brainstorming sessions, you can at one stage you may be able to decide these are the functions that sub functions that are required. Or you can look at the flow of material or energy or something like that, and decompose functions based on those signal flows. When you have completed the functional decomposition, then it is very important to identify what the critical set of subprograms, so that you could basically initiate your concept generation process from this critical subproblems.